Kia ora and welcome to Lecture 4. So today we start a block of 3 weeks on prediction. Prediction is the case where you have a numeric measure in a data set that you wish to predict from using other information in that data set. Later on we'll be looking at classification, which is also a prediction problem, where the outcome variable is a class, so it's a categorical variable rather than numeric. So we're going to start with prediction. And so a few definitions of things. The variable that we're estimating is typically called the target, outcome, or response variable. And the variables that we're going to use to estimate the target will be the predictors, the covariates, or the features. And typically to do this, we'll have a training data set which contains both the target and the predictors that we can use to build a model relating the target to the predictors, or the predictors to the target, however you want to think about it. And then we can use that model on a new data set, which is typically called the testing data set, which will only hold the predictors. So the goal then is to estimate the resulting target for that data set. Now the problem with doing this, of course, is that because the testing data doesn't contain the outcome variable, I mean the whole point of the process is to estimate what that what the unknown outcome variable is, we don't of course know whether we have it right or not when we're operating on the testing data, because we don't know what the right answer is. So for the purposes of developing a model, often we create an artificial test set, or what's sometimes called a validation set, so we can check how well our model's performing by, because on that data set we do have the answer, we do have the target variable. So we have both the predictors and the target. And often that's done by actually taking the training data that we're given and splitting it into two. So we might keep, say, 2/3 of our training data as real training data to build our model, and then 1/3 of it will be kept back as a validation set, so that we can compare. We will do prediction on that validation set and compare our predicted target with the actual target to see how well we do. So we're going to start by looking at some data on workers in the United States. It's quite an old data set. There's 400 observations of individuals, and we have their wage, which is going to be the target column. And then we have a bunch of other variables about them, some of which are numeric, like experience is the number of years I think that they've been working, perhaps, and then we have some categorical variables as well. And the goal then is to see if we can relate these predictive variables to the wage. So the goal is to predict the wage. So we're going to have an artificial test set, or perhaps we could call this a validation set, where we have those same predictors, but we also have the target here as well. So the real test set would not have the wage column, right? And our goal would then be to predict what the wage is for people we haven't seen before. But in order to sort of illustrate the process and see how well we're going to do with various model types, we're going to include the outcome variable so that we can compare our predicted results with the true results. So there's a huge number of models available for prediction, and we're just going to be sort of dipping into a few of them in this course. So we're going to start today with linear regression, which is something that you should already be familiar with. You should have done it in, touched on it perhaps a bit in first year statistics at university, and potentially a second year course as well. And then we'll also be looking at a couple of other methods. So we'll be looking at tree-based methods, so regression trees. We'll be extending that to forests, so a whole heap of trees all at once. And then we'll have a look at some very simple neural networks as well, to sort of get the idea of different model types. We'll be looking at a few more model types when we look at classification later on. But the ideas that we build up here will apply to any model type. And eventually we'll be using the Tidy Models framework, which allows you to basically put whatever model type you like in. Essentially it unifies the the code you use to build different models types. So essentially, as different prediction methods are developed, individuals that develop those tools and write the code to do to fit the models, we'll have a different API for dealing with that model. So a different set of code for dealing with that model. How the predictor variables and the outcome variable are put into the model might differ. The data structures might differ. How the predictions are returned might differ. Lots of things may be different between different model types that are developed by different people. Tidying models attempts to unify all of it. So essentially it hides the differences in the models, in the different sort of the coding criteria for each of the models. It wraps those essentially with a common interface so that everything is the same for each model type. Or at least the general things, the things that you do that are the same for each model type are the same. So the general approach with prediction is going to be using that training data to build some models. And the idea is that each of those models is going to be seeking to explain how you get from the predictive variables to the target. So the relationship between those things. And the process that we'll undertake is generally we'll construct a bunch of models, perhaps different model types or the same model type but different hyperparameters and so on, to try and optimize the model fit. And then we'll try and choose the one that provides the best predictions. So we're going to start with the linear regression model, which you would have seen before, though you may not have seen it presented in this way necessarily. So we're going to be using it in the multivariate sense. So we're going to be estimating an outcome y with a bunch of x's, which are our target, our predictor variables. And we may have multiple predictor variables. Okay, so we've got the I subscript is referring to the rows in our data. So those are individuals or individual observations. And then the second subscript on the x's is indicating what column. All right, so here I've got one predictor, two predictors, p predictors. Okay, so we're going to assume that our outcome variable, our target, is a linear combination of the predictors. So that means that we're just adding them up with constant multiples. And then there's going to be some error term, which is denoted epsilon I traditionally. And that's going to we're going to put some assumptions on the construction of this. So this is another way we can represent the same thing. So that sum over the betas, over the x's, can just be represented in summation form here. So it's just, all we do is we take each predictor variable, we multiply it by something, that's something we will estimate, and then we add them up. So the assumptions that we put on, so the assumptions that this is making is, first of all, that we've got this linearity thing happening, which is this, I guess, the strongest assumption is that we can just add the predictors up, and that will be a useful prediction of the target. So we're sort of assuming that a straight line relationship will eventually happen. We'll talk a little bit about what that eventually means later. And then we've got some error term, and we're going to assume that the error on average is 0. So that this is going to form an unbiased predictor of y. And we're going to presume that the errors are independent. So the rows aren't related to each other in our data, so our observations aren't related to each other. Or at least pairs of them are just as related as other pairs. And then we're also going to assume that this thing has constant variance. So the variance of the error doesn't depend on x or y. Okay, but it's constant across all our observations. So that's the normal 0 sigma squared thing. You may have been heard this referred to as line, L-I-N-E, linearity, independence, normality, and equal variance. Right, those are the 4 assumptions that we make. So the betas, they're our unknown coefficients that we estimate using the training data. So one thing to note is that all these x's in here are numeric, and of course in our data we had some categorical variables back here, right? So we put these into the model by encoding those categorical variables using binary indicators. So this is sometimes used called dummy encoding. And the idea is that we basically introduce a set of binary indicators for each categorical variable. The number that we introduce is the number of levels that category has minus 1. So if it has just 2 levels, you can use just one indicator. That indicator will be 0 and 1, dictating whether you're in the second group or not. So if it's 1, that means you're in the second group. If it's 0, you're in the first group. If you have 3 levels, like the race variable from our wage data had at levels of Hispanic, white, and other, then we can create indicator variables for white and Hispanic. Right, so just 2 indicator variables. And if the white indicator variable is 1, then obviously the race was white. If the Hispanic indicator variable was 1, then the race was Hispanic. And if both white and Hispanic are 0, then the observation has the other ethnicity. And this indicator variable setup is done automatically by the model.matrix function, which is called from LM. So it's done automatically for you. You don't have to worry about it. Now, it's not necessarily done automatically for you by other model types. So other model types might assume that everything's numeric to begin with. That's one of the things that the tidy models framework takes care of, is it provides an interface for doing this type of binary indicator variable construction. Another one that's a little bit different is called one-hot encoding, where you put an indicator variable for each group. So in that case, we're sort of over, those variables are going to be correlated because one of them is defined by the others, right? If you had a variable 1, 0 if it was Hispanic, 1, 0 if it was white, and 1, 0 if it was other, then the other variable is just guaranteed to be a 1 when the other two are 0, right? So they're 100% correlated. For some model types, that doesn't matter. For the linear model, it does. So linear regression makes quite strong assumptions, and those assumptions will almost certainly be wrong in most cases that we deal with. We'll see later on that doesn't necessarily matter. It sort of depends on how wrong things are, right? And so there's essentially 4 assumptions. So there's the 3 assumptions that we make on the residuals, which are that they're independent, normal, and of constant variance. And then there's the linearity assumption, which is sort of implicit in the fact that it's called linear regression. Now, I note that doesn't mean that it has to be a straight line, right? We can do transformations of the data first, right? So we can take our x's, for example, our predictors, and we can square them or square root them or take the log or exponentiate or whatever we want. Put a sign in, doesn't matter, because that process can happen before we put it into the model. The key is that the betas don't have a transformation. So it's linearity in the betas is the key. And again, you can put transformations on the y variable if you want as well. So you can model log y instead of y or whatever. And that's often a useful thing to do. So if your data look as though it behaves better on a log scale, then model it on a log scale, and then back transform at the end, right? Now, some of the other methods that we're using, like trees, forests, and neural nets, way more flexible than this. So they don't assume that linearity. Instead, they'll make some other assumption about the relationship between the predictive variables and the target. So how do we fit it? We have to estimate those parameters beta 0, which is the intercept, beta 1, the coefficient of x1, and beta p, the coefficient of xp, and so on, right? And we do this using the method of least squares, which is kind of the most efficient way of doing it, and it comes out of it sort of drops out of the mathematics to minimize the error. Okay, so if you look to minimize the variance of these things, then the method of least squares will drop out. And so we do this by minimizing the residual sum of squares, which is the sum of the squared difference between the actual y and the predicted y, which will be given by this. So you remember that predicted y is just going to be the beta naught plus beta 1x1 plus beta 2x2 plus dot 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 plus beta p xp, right? There's an error term on here, but we don't know what that is, right? And so this is basically the sum of the residuals, right? If you just take this equation here and you put all of this on the left-hand side, so you subtract, then we just get epsilon I, right? So all of this is doing is representing the sum of the errors, the sum of the squared error, okay, or the squared residual. It's squared because we want to, we don't want everything to balance out, right? If you had errors that are positive and errors that are negative, then of course this term could be 0 if you didn't have the square on there, or it could be negative or whatever. So the square ensures that this is that when this is smallest, we found our optimal betas. So this is done in R using the LM function, short for linear model. And the LM function takes a formula and a data set. The data is the data set here is a data frame for which it can use to pull out the column names that you specify in the formula. So the formula has the syntax here. So we're assuming that the target variable is y, so it's named y, a column called y in the data frame, and we've got other columns x1 and x2. Then the formula will be like this. Okay, so this is essentially the same as the linear model formula, the linear regression formula, except we've dropped the coefficients. So there's a beta 0 times 1 plus a beta 1 times x1 plus a beta 2 times x2. Okay, now by default you don't actually have to put the 1 in there because the LM function will automatically include an intercept, so that's equivalent to this. So y tilde x1 plus x2 is fitting a model with an intercept plus a term for x1 plus a term for x2. And a little shortcut is a lot of the time you're going to want to start by predicting your target with everything else. Right? And instead of having to type out all of the other columns in your data frame, because you might have quite a few, then there's a shorthand with the dot. So y tilde dot means model y with all of the other variables in the data frame. So if we just had x1 and x2 in the data frame, all of these formulas would be equivalent. Okay, so let's have a look at what we get when we model the wage variable with everything else. So my formula is going to be column name, so wage, all capitals, tilde dot means all other columns, and then I'm pulling my data equals wage.train so that it knows that when it sees wage, it's got to pull it from the wage.train, and when it sees dot, it's got to pull all columns that are not equal to wage from wage.train. So this step fits the model, so that is basically estimating all the betas, so it computes the residual sum of squares, minimizes that in order to estimate the betas using a bunch of linear algebra, and at the same time estimates things like the uncertainty in those parameters and so on. The summary function then gives us a overall summary of what the model is fit, and we get output that looks like this. So hopefully you fit a linear model in R before, and so this will be somewhat familiar to you, at least the overall structure. Perhaps you may not have done necessarily a one with many variables in it like this, but how we read them is essentially the same. So we can see that for each variable, each predictive variable, so we've got an intercept, right? So that's your beta 0. Then we've got a variable edu, which was the number of years in education, I think, which has a coefficient. So this is the beta corresponding with the edu variable. So it says that it's 0.8. So that means that for every one increase in the education number of education years, the wage goes up by 0.8 dollars per hour, which I guess is useful for us at a university that there's some relationship there. However, we note that there's quite a bit of error associated with that, and in fact the magnitude of the error associated with it is more than the magnitude of the effect. Right, so we think it goes up by about 81 cents per hour, but the error associated with it is over $1 per hour. So this, in fact, could be 0. Okay. But then there's various other things. So we've got some of these. So this, I think, was whether they're in the south or north of the US. This is if they're male or female. So we see the usual sort of bias here that males tend to earn more than females. There's the level of experience. So again, this is interesting that the level of experience doesn't seem to result in a significant relationship with the wage, in that the for every extra year experience, the wage goes up by about 26 cents, 27 cents, but the error associated with that is over $1, so perhaps it doesn't go up at all. There is a union effect, so being in a union seems to help. There's an interesting age effect is actually negative, so older people earn less, but there's huge error associated with that, right? And then there's various other ones, so let's have a look at these ones here, because these are the categorical ones. So we have the race effect. You remember race had 3 levels, Hispanic, other, and white. So we've only got 2 of them listed here because we only needed 2 indicator variables. So the Hispanic race is the baseline, if you like. So that's essentially included in the intercept term. And these are then differences from Hispanic to the other race and from Hispanic to white. And we can see that neither of these are significant. So this is the p-value on the end here. And you can sort of read it off by the number of stars, more better. And so you can see here that there's actually not really an effect of race here. So compared to Hispanics, other races earn slightly less, but there's a lot of error associated with it, so they could earn more. White race, obviously this is in the US, earns more, but there's quite a bit of error associated with it. Okay, management definitely does earn more, so we've got significance there, compared to whatever the baseline is here. I'm not sure what the baseline is. It'll be the group that isn't present in this list, so there are obviously 6 occupation classes. Professionals also earn more, sales earn less relative to whatever the baseline is, and so on. And if the person is married, yes or no. If they're married, they have a slightly better pay, but there's again a big error associated with that, so it might actually be less pay, not significant. Okay, and then this bit down the bottom, overall we can see that we're not doing terribly well with this prediction. The multiple R squared is essentially a measure of how well your prediction is doing. It's the proportion of variation in the response, so in this case in the wage, explained by our model. So you can see that we're actually only explaining 33% of the variation in wage using all of these predictors. So we're not doing terribly well. Okay, there we go. So the table contains estimated coefficients, standard errors, p-values for assessing importance. So linear regression models are a really nice way of modeling data for really 2 reasons. The first is that they're very straightforward and interpretable, in that the coefficients mean something, right? And so you can use them to understand the relationship between one variable and another, i.e. if I increase this variable by 1 unit, how much does the response change after I adjust for all of the other things? So you can quantify the effect of something with a linear model. The other thing is that they can be used for prediction purposes. So given a new observation that I haven't seen before, I can plug it into the equation just by putting the encoding the predictors in the same way, and then so for a new observation I know what my x's are, and therefore I can estimate my predicted wage just by plugging it into the equation, because I know what the betas are. And on top of that, because the linear model has lots of nice mathematics behind it, we know how these betas are distributed. So we know that each of them typically come from a t-distribution, which is sort of like a normal distribution, okay? And we know exactly what the standard errors are associated with it, so we can incorporate the uncertainty that we have about that prediction to give you a uncertainty interval with a specific level of confidence. So for example, we can say, we want to be 50% sure that the prediction is about our prediction, and so it'll give us a range of wages for which we're at least 50% confident that the true wage will capture the true wage. So how do we do this? The other models that we'll be looking at do not necessarily have this straightforward interpretability. So we'll see that regression trees do have an interpretability, so we'll see how that works. But as soon as we go to forests, that all becomes fuzzy. And neural networks, who knows what's going on, even in the simple ones that we're dealing with, which will only have sort of one hidden layer. We're not getting into deep learning here, which is even more opaque. But all of these models can do the prediction process, right? And so how do we do the prediction process for a linear model? We use the predict function. We throw our model in and we specify a new set of data to do the prediction. So the new set of data is going to be a data frame that has the same columns, the same predictor columns, and it will use the model coefficients from the model in order to, do the maths, right? Chuck it into the linear regression equation and spit out the answer. So by default, it's going to give us a vector of wages. So we have one wage per row in new data. We can also obtain our prediction intervals by adding an interval equals prediction as another parameter. So add a comma, and then interval equals prediction. And we can also specify the level of that prediction. So by default, prediction intervals will be 95% intervals. If you want something different, then another comma, level equals 0.9, say, for a 90% one. Okay, so how do we do it in practice? I would use this code here. So I'm running predict on my wage test data. So this is data the model hasn't seen before. It was trained on the training data, but of course we do have the outcome here, right? Because this is an artificial test set, it's not a real one. So we do know the true wage, and then I'm going to so we computed our prediction in pred. So pred is going to be a vector of numbers. It's going to be 8.38, 9.02, 8.50, and so on. We're going to bind that by naming it with bind columns. So this basically adds a new column to our wage test data, named .pred. I'm using the dot just for consistency with what comes later. I could have named this whatever I like, right? So that's equal to the pred vector, that one there. So that just adds a column to our data called .pred, and then I'm just rearranging things so that the wage and .pred columns are first, and then everything else comes later, just so that I can see it on my slide. So here's the true wage in the data, in the test data, and here's our predicted wage. And you can see just by eyeballing these that they do tend to sort of correlate, but aren't very good, right? So this higher one does have a higher prediction, but the actual correlation between these things isn't particularly strong. If we want a prediction interval, then we just add in the extra term interval equals prediction. Okay, and that will then return a matrix. So it'll have 3 columns. The first column will be called fit, which is the estimated wage. The second column is LWR, short for lower, and the third column is UPR, short for upper. Okay, so we have a named matrix, which we can use again with bind columns. Because it's named, we don't have to give it a name. And then again, we're just pulling out those 4 columns up front. So here you can see, here's the same column that we had before. So that's our best guess, if you like, as to what the wage is, given the model that we fit. And then these are the 95% confidence intervals. And what we can see here is that these are just horrendously big, right? So, we're estimating that this first person has wage $8.38 an hour, which is miles out. They only have wage $3.75. Perhaps they should ask for a pay rise. But the uncertainty interval is massive, right? So we're not 95% confident that their wage is somewhere between minus $0.1 an hour which of course is absurd. No one would pay to work, right? Up to $16.90 an hour. They actually get $3.75, right? So we've got a massively imprecise set of predictions here. Now, a tidier way to do what we've just done with the predict function is to use the augment function instead. So the Broom package is part of the tidy models framework and is a package that that's primary purpose is to get disparate output from models into a consistent form. So you would have seen already we've got two disparate outputs. So the predict function either returns a vector or a matrix. Two different things, right? That you've got to deal with in different ways. So if it was a vector, then I had to name the thing as I bound it to our data frame. With a matrix, I didn't have to because it's already got names. The augment function tidies that up. Okay, so there's not much to tidy up here because it's just a vector versus a matrix, not a huge issue. Okay, but in other model types, it might be quite a big issue. And so the augment function, you give it a model, you give it a new set of data, it will do the prediction for you, and it will bind it to the test data. So it adds a new column to the test data using the prediction. Essentially what it does is it augments the test data with information from the model. So in this case, the prediction from the model. And you can do interval prediction in the same way that you would for normal predict. The other advantage that augment has over predict is it is the same across model types. So, for example, back here, the linear model form of prediction, so the predict function for the linear model returned columns of fit, lower, and upper. Other model types might give you a matrix with 3 columns, or might give you a data frame with 3 columns, or might give you something else. Those columns needn't be named the same thing. With augment, they're always named the same. So you always have dot fitted, and if you've got an interval prediction, dot lower and dot upper. Okay, and you may have other things as well. So you can see here that there's some other stuff here like dot resid, various other things that are given to you. Okay, so same output, but in a sort of tidy models type framework. We'll see a different way of doing this in lecture 6. So given this nice tidy data frame, we could actually visualize this because we could visualize the actual wage versus the prediction here. And so I put the predicted wage on the x-axis and the true wage on the y so that I can plot the predicted wage versus true wage, the dots, and then I can put the prediction intervals on as well. So I'm doing this with geom line range. So geom line range takes an x, a y min and a y max, or a y, an x min and an x max if you're doing them horizontal instead of vertical. Okay, so in this case, for each fitted observation, okay, I produce the range that we think is going to capture the true wage, and then I'm putting points on, which is the true wage and the predicted wage. So we can see that this is not a good effort at all for 2 reasons. The first reason is that if we, what we would be expecting here is a nice increasing trend between predicted wage and true wage. So if we just look at the red points, we can see that there's a huge amount of variation here. Right, so for a given predicted wage of, say, like here 12, you've got a true wage that's actually about $1, and then you've got another one which is about $22. So we're getting miles out. Okay, so we're doing a very poor job, and you can see that the uncertainty is huge as well. So for example, with a predicted wage of, say, 12 again, we're predicting their wages somewhere between $4 and $21 an hour, which is not a very useful range, right? I mean, it's just basically almost everyone earns between $4 and $21, so there's very little relationship between these two things. And we had a hint of this back when the multiple R squared was just 0.3. So we've only explained 30% of the variation in wage using this model, so we shouldn't expect the predictions to be any good. Okay. Now, of course, there's a fundamental problem here with this model in that some of the prediction intervals are giving negative wages, which is just ridiculous. So because we know that the true wage should always be positive, one of the things we might want to do in this case is log it first. So look at the log wage versus the predictors. The advantage of doing that is that when you undo the log, you exponentiate. The result from an exponentiation is always positive. So our prediction intervals would never go below 0, which is more realistic. Okay, so that's something you might want to try if you like. Okay. So the wide prediction intervals indicate that we've got a huge amount of uncertainty or lack of precision in our predictions. And we might have thought, we have 400 rows in our data and we've got 10 predictors. We might have thought we might do better. And it could be really down to two things. The most likely thing is that wage is just actually very difficult to predict using the attributes that we have. That's probably exactly what's going on. We'll try some other model types later on the same data set to see. Part of the problem, though, is we may be including variables that aren't related to wage or are only very weakly related to wage. And including things that aren't really relevant means that we need to estimate the parameters, right? Estimate the coefficients of those predictors, estimate the betas. And to do that, we need to estimate their uncertainty. So we're essentially adding noise and reducing precision. So it's plausible that a simpler model, one that removes variables from the model, may actually improve things. And it comes down to the bias variance trade-off. So the idea here with the bias variance trade-off is that errors in our prediction arise from both of those things. So bias is systematic error in that the average error differs from the error differs on average. So essentially the mean prediction differs from the mean target, conditional on X. Whereas variance is a measure of essentially the uncertainty in the estimated model parameters. And so we'll look at an example where this might happen. So suppose we have a target variable y and two predictors, x1 and x2. And suppose that the true relationship between these variables is that y is in fact predicted in a linear sense from x1 and x2. So there's a linear relationship between x1, x2, and y. So just beta 0 plus beta 1 x1 plus beta 2 x2. And that the unpredictable bit of it, the errors, have average 0. So on average, we are getting a correct y. And we can see this by if we just take the average of y. So this is expectation of y. So the expected value of y is just the average of y. The expected value of y is just going to depend on these things. So if we know what the betas are, then none of this is random. Right, the only random bit is the epsilon, therefore y is random because it depends on epsilon. So the expected value of y is just, this isn't random, so it's just equal to that thing. Expected value of a constant is a constant, plus the expected value of the error. And if the expected value of the error term is 0, then the expected value of y is exactly given by the linear predictor. Right, so the true regression equation is estimating y correctly on average. Right? It's not going to be perfect for every y because, of course, y is going to have some error in it. Okay, but on average, it's going to be correct. So if you think about it in terms of what the picture of y versus x1 and x2 looks like, you're going to have a straight line relationship between y and x1, but there's going to be scatter about that line. But the trend is going to be completely correct. There's going to be no curvature or anything like that. So we're going to fit this equation, we're going to fit a regression model to this equation. And it turns out that when we do so, the least squares estimators that we compute, so the estimates that we get for beta 0, beta 1, and beta 2 are unbiased. So that means that, that the expected value of beta 0 hat is exactly the truth. So on average, when we fit the model to a sample of data, we're going to get the correct value in the population, if you like, for the intercept and for the slopes. And so that means that when we compute the expected value of a predicted observation, we're going to get it correct on average. So if you have a look down here, we've got the expected value of a predicted observation y hat naught. So that's just going to be our estimated coefficients from fitting our model times the observed predictor variables for that observation. And so when you do the expected value of this, expected value of a sum is the sum of the expected values, so you can split the expectation over these terms. Then x is not random, right? It's a fixed value from our data, whereas beta hat 1 and beta hat 0 and beta hat 2 are random variables because they come from a sample. Choose a different sample, going to get different realization of these random variables. So the expectation of this product here is just basically a constant x1, 0 times something random. So it's just the expectation of the random thing times the constant. All right, so you can split that expectation up. And then we know that because these things are unbiased, it just drops down to the true population value, the true coefficients from the population. So the expectation of our predicted y is just equal to this expression here, which is the true unobserved target, except for the error. Right? And of course, the expectation of y0 is just equal to the truth plus the expectation of the error. The expectation of the error is 0, and so these two things are the same. Right, so on average, the predictions from our linear model are going to be unbiased. So our bias is going to be 0. But the variance of prediction, of our prediction, is going to depend on the variance, the standard errors, correlation, and so on of these beta hats. And so if our functional form is correct, then our regression model is going to be unbiased, so the bias is going to be equivalent to 0. However, if we got the functional form wrong, but we still fit a linear regression model, so say for example that we only estimate y using one of the variables, so say x1 instead of x2, then the functional form is wrong because we'd be assuming that the coefficient of x2 is 0, i.e. x2 has no influence because we're only estimating y using x1. So we'd be assuming that the coefficient of x2 is 0, x2 has no effect, we're not including it in our model, when in fact x2 might contribute to the outcome variable y. So that's one way to misspecify a model, is to include variables or leave variables out that are important. The other way is the whole linearity thing. So we might be assuming the functional form is linear when it's not, right? So perhaps the true form of the equation might have a square in it. Okay, we could still fit this with a linear model because it's still linear in the betas, but unless we configured it that way, when we wrote out our linear model formula, it's not going to be fitting that particular functional form. But if we get the functional form right, the linear model is unbiased. Now the trick here is that because the variance of the model depends on the uncertainty in the betas, sometimes it's better to get the functional form of the linear model wrong, i.e. by intentionally misspecifying the model, to introduce bias if the consequence of that is that the variance is reduced. So let's have a look at an example. So again, we're going to use y related to two variables x1 and x2, and we're going to compare two models. The first model is the correct one. So we're going to say that y is equal to some linear combination of x1 and x2. And so we're going to fit that model, which is correctly specified. And then we're going to fit a simpler model, which relates y only to x1 and ignores the contribution for x2. Then if x2 actually does have an effect, then the second model here is going to be misspecified and therefore biased because it's not including that effect, right? We're assuming whatever the effect of x2 is, we're ignoring it. But there's a case where perhaps x2 has an effect, but it might be small. Then if the effect of x2 is present but small, then model 2 is only missing that small effect. And maybe that's not too bad. So model 1 will be unbiased, but because the effect of x2 might be small, then we have the extra burden of estimating the additional coefficient beta 2, which we then know is going to be a small number, but may have quite a bit of uncertainty associated with it. And that uncertainty might give rise to higher variance from model 1. Model 2 we know is going to be wrong, right? It's going to be biased because we're not including the effect of x2. But the effect of x2 is actually small, so by not having to estimate it, we may reduce our variance. So we're going to be biased, so that's going to be a problem, but maybe we'll have lower variance. And those two things can trade off against each other. So let's have a look at just simulating some data from a known population and then fitting these two models and seeing what happens, right? So we're going to simulate 150 observations of x1, x2, along with some noise, and then we're going to compute what y is. So y is just going to be literally that exact equation. Okay, we're going to specify, we're going to know what the coefficients are beforehand. The idea is that we're setting it up so that the intercept and the effect of x1 are magnitude 1, whereas the effect of x2 is 1,000-fold lower. Right, so x2 contributes to y, but 1,000 times less than x1 does. Then, once we've done, we're going to split it into a training and test set and fit our model. So here you can see the setup. So x1 is just uniform, is just a standard normal, 150 instances of standard normal. So is x2. So is our noise term, okay, which has less variance than the x1 and x2, and then we've computed y. So we know that y is related to both x1 and x2, but the effect of x2 was much less than the effect of x1. Okay. So when we plot our data, we get exactly what we'd expect, right? So if we plot y versus x1, then you can see that we've got a clear increasing relationship between y and x1. And if we plot y versus x2, we've got a very unclear relationship. Whatever relationship there is not strongly predictable from x2 to y, right? We can predict y from x1 relatively easily here because we can see that as x1 goes up, y goes up. Whereas it's much harder to see the relationship between y and x2. Notice the code that I've used here. This is a common way to generate scatter plots of one variable versus many. So all you do is you pivot your two variables that you wish to plot longer, and then you so that will basically produce a column that says which variable it is, x1 or x2, right, which is going to be the name column here, and the value will then go into a value column. And so now I just plot y versus the value column and can facet by the name column. So I've got a x1 versus y and x2 versus y automatically in one plot. Of course, I could just do two in this case, right? I could have just taken my original data and did a ggplot with x equals x1, y equals y, and x equals x2, y equals y separately, and then combine them with patchwork or something. So we're now going to fit two models. We're going to fit our true model, right, which we know is correct, is unbiased, y equals x1 plus x2, and then we're going to fit a misspecified model where we ignore the effect of x2. So model 1 we know is going to be unbiased, model 2 is going to be definitely biased because it's misspecified, we're ignoring x2. So we're then going to have a look at the predictability, how well these models do. So we're going to pull out the R squared. So glance is pulling out the bottom 3 rows from the linear model summary. So you remember that the linear model, if you run summary on a linear model, you get your block of coefficients, and then underneath that you have some information on the overall model fit, including the R squared. Glance is the Broom function, so same as augment is, that pulls just that information from the bottom row. Again, in a tidy fashion, so it will always have similarly named variables. So for example, we have r dot squared for the multiple r squared. So you can see that model 1 has multiple r squared 0.7222755. Model 2 has a lower, not much lower, but lower, right? And this is because it's misspecified, right? We've got more information in model 1 because we're able to make use of x2. So model 1 has a better fit, a higher r squared. We're explaining more of the variance in y than we are using model 2. However, if we look at predicting on the test set, so you remember we split our 150 observations into 100 training observations and 50 test observations, so we can do our prediction on those 50 test observations. So I'm going to do that. So I'm using augment on model 1 with our new test data and prediction interval, and augment on model 2. I'm binding those as separate rows into a single data set. So I'm going to get a prediction from model 1 and a prediction from model 2. The ID equals model essentially means that I get another column called model, which will be filled in with model 1 or model 2. And so essentially I get 2 blocks of prediction in a data frame, right? So I get 50 rows prediction from model 1, 50 row prediction from model 2, and I get another variable called model saying which row comes from which model. So model 1, model 2. And then I'm computing the prediction interval length, which is the upper minus the lower, and I'm plotting them, split up by model. And so what I notice is that the length of my prediction intervals for model 2 are consistently lower than the length of the prediction intervals from model 1. So you remember, model 1 was unbiased. We were including the effect of x2. Model 2 is biased because we're ignoring the effect of x2, but the prediction intervals we get from model 2 are shorter. And the reason is that we haven't had to estimate the effect of x2. And because the effect of x2 was small, our overall prediction interval length is still shorter. So even though we're biased, we've got less variation, less uncertainty in this model. And it turns out that the lower variance that comes from model 2, because we don't have to estimate that extra coefficient, which we know doesn't have much effect, that actually offsets the increased bias, right? So model 1 has lower bias, right? Because it's the correctly specified model. Model 2 has bias, but it has less variance because we haven't had to estimate that extra parameter. And it turns out that those two things essentially cancel out. Well, they do better than cancel out. The reduction in variance is actually means that the overall performance of the model is slightly better for model 2 compared to model 1. Now there's not much in it. Here's the mean square error. So the mean square error is a way to estimate how close we get to the right answer. So you remember when we've got our predictions on our artificial test set, we know what the truth is, the y is, for that artificial test set. So we can compare y to our estimated value, which is the fitted value. And so this is the mean square error. So it's how far out we are. Essentially, it's the variance in our prediction. Okay, and you can see here that the mean square error in model 2 is slightly less. There's nothing in it really than model 1. So even though model 2 was biased, the reduction in variance was enough to offset that bias such that we got very slightly better predictions than in the correctly specified model. So by deliberately misspecifying the model, we did slightly better. And this happens in practice, not just in simulation. And the idea is because the mean square error for prediction essentially breaks down into bias and variance. And so by increasing one of those things, you might decrease the other such that you overall improve the mean square error. Okay, so this is the idea with mean square error. So we've got some target y, which we're predicting using x1, x2, and xp, and so on. Okay, and we've got some functional form, which for a linear model might be a linear prediction, right? It might be beta naught plus beta 1 x1 plus beta 2 x2, and so on. And then we've got some unpredictable error term. Okay, now let's assume that the unpredictable error term has mean 0. So on average, y is related to some functional form f. Then the whole point of fitting the model is to estimate what f is. Okay, and so we're going to train some model on our data in order to estimate f. We might have some f hat. So if this was a linear model, right, we'd be assuming that f has a linear functional form, and then f hat would be the same functional form with our betas in it, right? Or our beta hats compared to our betas. And the ideal thing is that f hat looks something like f, right? The thing we're trying to estimate, the functional form relating our predictors to y, is trained nicely on our data. Then the mean square error is just the expected squared error between these two things. Okay, so it's just the squared error on average, if you like. And it turns out that those things can be decomposed directly into variance and bias. And this is the maths. If you haven't seen this type of thing before, it looks quite kind of scary when you first see it. Let me break it down because it uses kind of a common trick. Essentially, all of this maths depends on three things really. The first thing is it depends on a trick, which I'll show you in a moment. The second thing is it depends on the quadratic formula, or how to expand a square in brackets, right? So a plus b squared equals a squared plus b squared plus 2ab. That's what it depends on. And the third thing it depends on is the concept of expectation and how that breaks down. So for example, the expected value of a sum is the sum of the expected values. The expected value of a constant is a constant. The expected value of a constant times a random variable is the constant times the expectation of the random variable, right? So just the properties of expectation is all it depends on. Now the trick is this very first step here, right? So here's the thing we want to evaluate. It's the expected difference, the expected squared difference between our estimated functional form relating y to x and the true functional form, which we don't know, right? And the trick is to subtract and add something. This is a common thing that you'll see over and over in sort of the mathematics of statistics. You'll see it later on, perhaps when we look at clustering. Same thing happens there. Okay, where you subtract something and then add it back in, right? So we're adding nothing here. This expression is the same as this one. All we've done is we've minused off this expected value of f hat and then added it back in. And then we use our quadratic. So we treat this as our a, and this is our b. So we've got a plus b all squared. So we're going to get a squared, which is this bit here, plus b squared, which is this bit squared here, plus 2ab, which is that bit there. The next step is to note we've got the expected value of a sum. So you've got the expected value of this, plus the expected value of this, plus the expected value of all of this. Okay, so we can split it up into the expected value of this bit, plus the expected value of this bit, plus twice the expected value of this bit. So this is using the rule that we've got a constant 2 here that we can bring outside the expectation, right? Because you're just scaling something by 2, So the average will scale by 2, right? Then again, we use the property of expectation. So this term here is going to stay the same, but if you look at this term, then here we've got the expected value of a random thing, f hat. So this is just now a constant. There's no variation left in this because we've already taken the expected value. Right, so this is just the mean of that thing. F is again a constant. It has no, it's the true relationship, so the expectation is constant. And so when we compute the expectation, so this entire thing is no longer random. So when we compute the expectation, we just get the same thing that we had before. It's just a constant, and so the expectation drops out. When we look at this, again, we've got that same term. So this term here is a constant. Okay, we've got the expectation of a random variable. That is now a constant, and then f is also a constant, right? It's not random, it's the true relationship. So again, this is a constant that we can bring out of the expectation, so we only need to run that expectation over this term. And then again, this is a constant, this piece here. So that piece there is a constant, and so the expectation is just expectation of f hat minus that constant. And when we do that, we see that we've got 0 here. And so this term drops away and we just get these two sums. Okay, so the purpose of adding and subtracting in here was so that we got that cancellation down there. Okay, we'll see the same trick when we decompose the Euclidean distance squared thing when we look at the k-means clustering process. So the mean square error turns out to be to decompose directly into these two terms. And if you look at these two terms, this here is the bias squared. So you remember the bias was just expected value of f hat minus f, just the difference between our predicted value on average and the true value. So this is just the bias squared. And then this here is the variance. So if you just look at this, this is literally the formula for the variance of f hat. Right? If you look at the formula for variance of x, it's just expectation of x minus expectation of x squared. Right, so the mean square error decomposes into variance and bias. So mean square error is a measure of predicted performance, and that depends on both the variance of the predictor, of the thing that we're trying to fit, and its bias. And so because of that, by deliberately misspecifying the model such that the bias goes up a little bit, if you do that in a way that reduces the variance, and if the reduction in the variance is more than the worsening of the bias squared, then the mean square error will go down. So the bias variance trade-off here is always in play because the mean square error literally decomposes into their sum. Okay, so accepting some bias is advantageous if it results in a substantial decrease in variance. And usually what happens is simpler models have less variance. Simpler models are almost always going to be inaccurately describing the true relationship because they're simple, right? So they'll tend to increase bias, but they'll lower variance. And if the increase in bias is less than the decrease in variance, then you're better off. So that gets us to model selection. So model selection is really important for obtaining good predictions. And one of the key ideas of model selection that we'll be looking at as we look at different model types is which model type we should use. Like, should we use a linear regression? Should we use a random forest or a neural network or something else? But there's a second aspect, which is given we've chosen a model type, so say we choose a forest or a linear regression or whatever, then there's still more choices to make because there's ways to sort of optimize that model. So for example, with linear regression, what set of predictors should we include to try and minimize the mean square error? So our goal in prediction is always to get the best predictions possible based on some criteria. So for example, based on mean square error. And we know that if we include more predictors in our model, then we'll tend to reduce bias because it's likely that those predictors are related, at least in some way, to the outcome variable. But by including more predictors, we're going to have to estimate the coefficients, which is going to increase our variance, right? Because we have to include the uncertainty of those things. So choosing which model to use, which predictors to use in the model, is tied to the bias variance trade-off. So if we go back to the wage data, you'll remember that when we fit that model, that race wasn't important. Right, so if we go right back to our summary, we see that the coefficients for both of the effects for race were not important. Our p-values were large. So one thing we might try is, well, just removing it. So our model is suggesting that race is not important. So we could refit the model without race and see how we do. So one thing we could do is we could fit a new model, so LM2, which is wage in terms of everything minus race. So this is one way of saying I want to include everything except a variable. Then we could do prediction with wage.lm2, which is our model without race, and wage.lm1, which is our model with race. And we could do that prediction on the training data, and then we could compute the mean square error on the training data. And when we do, we find that the mean square error of model 1 was 16.6, and the mean square error of model 2, the one without race, is 16.7. So by removing race from our model, we've done worse on the training data. But what about if we look at the test data? So you remember we have this artificial test set, which hasn't been used to train the model, hasn't been used to estimate those betas. We could use our prediction on that and compare it to the true value of the target variable wage, right? So we're going to take our wage test data and bind predictions on the wage test data, and then compute the mean square error in the same way. And we find that the mean square error from model 2, which is the one without race, is now less than the mean square error from model 1. So on the training data, we should prefer the model with race included, but on the test data, we should prefer the model without race. The other thing we note is that the mean square error is quite a bit bigger for both models, right? It was 16.6 on the training data, 21.9 on the test data. Quite a big difference. So two things are going on here. One is that the mean square error is higher on the test data compared to the training data. And the second thing is that the mean square error of the model without race is better on the test data, but the mean square error of the model without race is worse on the training data. And why is that? Well, what it comes down to is that is basically the fact that we're predicting on the same data set that we're training on if we're looking at the training data. And that gives biased results. And the reason is that our model was constructed using the training data. So the coefficients that we've computed, the betas, are specifically tailored to that data set. So if you like, if we're then using that data set to evaluate how good the model is, of course the model does well, because the model was trained on that actual data set. If you like, in a sporting metaphor, you've got home ground advantage, right? Where, you know, everything is familiar and therefore you tend to do better on average. And you can show that this is the fact just by computing the mean square error. So you do a bit of maths. If you work out what the mean square error on the training set is, then it's just the difference on, you know, the squared difference between yi and yi hat, i.e. the predicted value and the true value, which is just the residual sum of squares divided by n. Okay, the residual sum of squares is this bit, isn't it? So it's the average residual sum of squares, essentially. And removing predictors, like we've done by taking the wage away, can never reduce the residual sum of squares. it will generally cause it to increase. And so the mean square error of training data will always favor a model with more predictors. And the reason is that it fails to account for the bias variance trade-off, because the only thing it's looking at is bias. It's not looking at variance at all. So in practice, we'll want to evaluate model performance on a separate data set, a validation data set. Now, usually that won't be our test data. So our test data will usually be a data set that doesn't have the target variable in it. Right? So we can do prediction on it to predict what the target variable is, but we don't know what the target variable is, so we can't compare how well our predictions do with our actual variable. So in practice, what we'll end up doing is we'll be given a training data set, i.e. a data set that has the outcome variable and the predictors, and we'll split it into two. One part we'll use to build the model, and the second part we'll use to validate the model, or to estimate model performance, if you like, to compute reliable mean square error. Okay. So if we did that with the wage data, then we could treat the test set in this case as a validation set, because the test set was an artificial one. It actually had the response. We see that the mean square error computed on that test set is larger than the mean square error computed on the training set, and that's because we've lost that home ground advantage. In addition, we found that the model without race performed better than the model with race. Okay, so by intentionally simplifying the model, so it's completely plausible that there's a relationship between race and wage. People are racist in general, right? So that's completely plausible, and we've ignored it in the construction of Model 2. Yet we've done better for prediction. Okay, so we've intentionally reduced bias, and by doing so, we have reduced the uncertainty. Now, we haven't reduced the uncertainty much in this case. We've still got a very poor model, but nonetheless, it's a better model than the one we had to start with. Now, there are some alternatives, particularly in the case of a linear model. The mathematics of the linear model are such that you can construct model selection methods that aren't based on aren't based on mean square error, and therefore take into account the bias variance trade-off. And the most common is the Akiki information criterion, which is often abbreviated to AIC. AIC. And it's basically a measure of model quality in that it trades off the concept of model fit with model complexity. So models that fit well will have a higher AIC, and models that are more complex will have a lower AIC. So simple models that fit well are favoured over more complex models that only fit a little bit better. So the bias variance trade-off is in effect there, because if you increase the model complexity, you might be reducing bias, but you've got to estimate a bunch of things. So you're increasing variance. Whereas if you decrease model complexity, you might be increasing your bias, but decreasing your variance. So AIC has the property that the lower the AIC, the better the model. And it's often used in a backwards variable selection algorithm, or a forwards variable selection algorithm, or a stepwise algorithm. So we're going to look at backwards selection, but the same ideas apply. And essentially what happens is you start with a model with everything in it, and then you compute the AIC. You then remove each variable in turn, compute the AIC for each one, and then decide whether you should take one of them out. So this is the process. So you fit a model with all predictors, compute the AIC. You remove each predictor in turn, refit the model, and compute the AIC again. So those models are your options for the next step. Then you compare your AIC of the current model with the AIC of the AIC of the candidate models, and if you can improve things, i.e. if you've got a lower AIC, then you choose choose the candidate model with the lowest AIC and repeat the process. So with the wage data, you can use the step function for this. So you fit a model, which will be the full model, and then you run the step model, which does backwards variable selection, and it spits out a bunch of stuff. And so this is what it starts with. So here's the first model, which is the full thing. So that's wage.lm. And then what it does is it says, well, what happens if we remove the married variable? Then our AIC will be this number here, 1156.1. What happens if we remove the age variable? Our AIC will be very similar. The experience variable, it'll be a bit bigger, and so on. If we did nothing at all, that's this one here, that's our current AIC. All right, so it computes the AIC for the current model and all of the options of removing one variable from those models, and it then ranks them. And so the idea is that when we move to the second step, we're going to remove married. So the second step, you can see here, doesn't have married as our as an option. And so now it's going to say, well, okay, what happens if I do nothing from here? So that AIC is the same as the AIC up here. But what I could do is I could take out age, and I would improve my AIC further. Or I could take out experience or race and so on, right? Notice that if it tries to take out occupation, it gets worse, right? Because occupation is telling us quite a bit about the wage, and so on. So it keeps on doing this until the none model ends up on top, i.e. no change is better than a change. So the final model includes these terms here. So you can see that race is in fact removed. So this is the final model. So this is a summary of the final model table. Notice I'm using the tidy function here. So tidy gives you a data frame, or in this case a tibble, saying basically the same thing, which is that coefficients bit of the summary. So the summary output from a linear model gives you kind of three separate things. Well, no, two things really. It gives you the coefficients table, and it gives you a bunch of stuff about model fit. So the tidy information pulls out the tidy function pulls out the coefficients into a data frame that you can then use, like for plotting or whatever. The glance function pulls out the information on model fit, like your multiple R squared and overall p-value and whatnot. Okay, so those are the final things. So you can see here that some things are still included that you might think might not be. So for example, this one here. So we've got sector manufacturing. You can see that the p-values for both entries here are reasonably high, yet this has still been included in the model. Similarly, the south effect, the p-value is reasonably high, yet it's still been included in the model. And the reason it's still been included in the model is that taking it out increased the AIC. Right, so there's a bias variance trade-off here where, yes, including it in the model meant we had to estimate its effect, and its effect in the linear model wasn't all that important if you compute, if you evaluate it using the p-value. However, the AIC obviously decided that, by the AIC criteria, including south was slightly better than not. So now we've got three models. We've got wage.lm, which was the one fit on all of the variables. We've got wage.lm2 where we removed race, and then we've got the result from our AIC stepwise elimination, wage.lm.step. And we could then compare all of these on our separate test set for which we know the answer. So here I'm taking our test data, I'm binding a prediction from each one, and then I'm computing the mean square error across all of them at once. So this is something you may not have seen before in dplyr maybe. If you want to do an operation on multiple columns at the same time, you can use the across syntax. So here we're summarizing across all the rows that begin with wage.lm. Notice that I named them wage.lm, wage.lm2, wage.lm2, lm.step, so they all start with wage.lm. And then the function that I'm applying is done in this lambda syntax. So a tilde, which specifies this is a function, and the function then takes a dot argument, which is equivalent to this is like f of x, right? And so each of the columns, wage.lm, wage.lm2, wage.lm.step, will be substituted in for the dot, and then we'll subtract off the wage column, square it, compute the mean, right? So this is a mean square error computation. So now you can see that I've computed mean square error across all three at once. So you can see I've got 21.89, that's the original, 21.88, that's the one where we removed race, and 21.921. So you can see here in this case, wage.lm2 is the best at prediction on the test set. But they're all really similar. So removing variables hasn't really improved things massively. Okay, so we'd have to perhaps, I mean, you know, if you were trying to choose the one that does the best prediction, you'd choose wage.lm2, but there's not a huge amount to suggest that any of them are much better than the others. We'll see if we can do better with different model types in the next lecture.